Let's move into chapter 5. We're going to talk about probability distributions. Now, probability distribution is how you describe the probability of certain events within an experiment. Now, there's a couple of requirements for your probability distribution. Let me list those here for you. First requirement is that for each of your probabilities for some event X is between 0 and 1. That is a necessity. So that's one requirement. The second requirement is that when you add up all these probabilities, the sum of everything that can happen has to equal 1. Now there might be a little bit of rounding error here and there. That's okay. But overall, that total should be pretty close to 1. Let's look at a couple examples of such. We'll start with example A here. And a simple question that I could ask you on an exam would be, is this a probability distribution? Or I could ask you to fill in these values to make it a probability distribution. So remember that your probabilities have to be between 0 and 1, and that the total has to be 1. Now I'm not really into making you add these things up manually, so let's head over to our Google Sheets. If you click the bottom left tab, tab A, you can see that I've already placed the sum in here. The sum of these 5 terms, actually 6 terms, is exactly 1. So great. And since each of these probabilities is between 0 and 1, then wonderful. This is a probability distribution. So the answer to that first question is yes. But we're going to go a little bit beyond that and work with not only is it a probability distribution, but we're going to find 2 other things about these probability distributions. The first one is mu, the second one is sigma. Do you remember this notation? What do these Greek letters mean? What's
the mean and standard deviation?
Yeah. First one is your mean, second one's your standard deviation. We're going to need to find the mean and standard deviation for your probability distributions. So let's work with it with kind of a funner example, which would be example C down here. And that is rolling some dice. We're going to roll 2 6-sided die. So there's 6 outcomes here, and there's 6 possible outcomes here. How many events are there all together? How many different possibilities can you run into when you're rolling 2 6-sided dice? 36, right? So that's going back to our counting rules from the first section. 6 times 6 is 36. There's 36 different possibilities here for the simple events that make up this experiment. Now the probabilities are already listed for you here, and I've got them listed in a couple different ways. Google Sheets doesn't really understand fractions, although I did write them in as fractions. What do you think is the most likely roll when you're rolling a pair of dice? What's going to come up most often? There is one. It's one that's a little bit more likely. Take a look at the probabilities here. Which one looks most likely? 7, right? 7's going to happen 6 out of 36 times on average. You've got 1, 2, 3, 4, 5, 6 ways to roll a 7. You've only got 1, 2, 3, 4, 5 ways to roll a 6. So the 7 is the most likely roll to happen. Now, are you guaranteed a 7 when you roll a pair of dice? No, no. But it's the most common roll. Let's figure out, what what the roll is on average when you're rolling a pair of dice. And so let me explain how to calculate the mean of a distribution. Mu is going to be the sum of x times p of x. So x is your column over here, That's the or that's the actual value of our variable. And then P of X is its corresponding probability. So its corresponding probability, we're going to use it as a decimal. This column times this column, that's what gives you this, X times P of X. And it's the sum of this column right here that gives you the mean of that variable. So let's take a look at how to calculate the mean of that variable from a probability distribution. So click over to example C, please. Should give you the chart that you just had up. And what I want to do with you is plug in some of these numbers here, or get Google Sheets to plug in some of those numbers for us. So I want to start right here in column E. Column E, row 4. And for this, I want to put in X times P of X. X times P of X. Okay. What do all Google Sheets commands start out with? Equals. Well done. I want this one, which is A4, times, now to get the times key, you hit Shift 8, that'll give you a nice asterisk, times P of X. Choose it from this column, D with the decimal, not from C with the fraction. Unfortunately, it's not going to understand fractions. So I'll zoom in a little bit. If you want to see that, it's A4 times D4. When you're ready, press enter, and it'll probably offer you the chance to do this all the way down, right? Mm-hmm. All right. So yeah, just click yes. Then what you're going to want is the sum of that column. Well, I think I already put that in for you. So the sum of that column is 7. What does that signify? That's the mean. That's your average roll. If you were to sit at a table and roll a pair of fair dice thousands and thousands of times, on average, you're going to roll a 7. Okay, not terribly surprising here. One thing to keep in mind is that this is just a numerical calculation. It doesn't necessarily always have to be a value that you can get from your experiment. If I did the same calculation with 1 die, my average roll would be 3.5, which you can't even get with a single die. But that's still your average. On average, you would be rolling 3.5. Are we okay with our calculation of the mean? Let me share with you some more calculations that we're going to do here. Oz?
I don't know how to formulate the question.
All right, we'll think on it, and if it comes to you, let me know. Does anyone know what that symbol is? That's your sigma again, but what does happen when we square sigma? What do you get when you square sigma?
Variance.
Ah, well done. This is the variance. That's your variance. The variance calculation is a little bit messy. I won't lie to you. It's the sum of P of X times X minus mu squared. That's how you're going to calculate the variance. From the variance, I can get the standard deviation. What do I do to get from the variance to the standard deviation? Square root. Well done. So it's going to be the square root of all this. Sum of P of X times X minus mu squared. All right. Let's see here. Going back to this distribution, now we got this messy calculation to type in. I've given you the format of it right here. It's P of X times X minus mu squared. The one thing I strongly suggest is that when you type in this formula, you don't click down here to get the mean. You just actually type in the number. That's always when you use these formulas. Without getting technical, if you click down there to get the mean, it's going to mess you up. So actually physically type in the number. So it's going to look like this, equals. Where do I click to get P of X? What column? D. D4, good. Times, what do I get to do the times? Shift 8, good. Left parenthesis, so keep your finger on that shift key. X, where's X? What column's X in?
2.
It's in column A.
Oh, I'm sorry.
Minus, and this is where you got to type in the mean. For us, it's pretty easy. It's just a 7. Minus 7, and then right parenthesis, shift 6, and then a 2. That gives you your squared. So let me zoom in on this a little bit so you can see that calculation up here. That's what you should have in your Google Sheets. I'll pause for a second. Everyone got that one? D4 times parenthesis A4 minus 7 parenthesis squared. All right. So that gives me 0.6944. Is that what you guys are getting? All right. So I'm going to click, yeah, go ahead, do that for the rest of the formulas. And if you add that all up, which I've already done for you, if you sum that up, then you're going to get 5.8 something. Well, that's the variance. That's great. If you want to get the square root, then you want to click down below, type in SQRT of the one up above, and that'll give you the standard deviation. So the standard deviation, let's see, I didn't mean to do that. There we go. Standard deviation, I'm getting about 2.4152. Is that what you guys are getting? Quentin, did your battery die?
Yeah.
You can try and find a plug someplace. What, you didn't bring your charger?
No.
Ah, sorry. Yes?
Can you repeat the real quick, or just click on it? I can see it.
So the variance is the sum of this column. All right, so when you finish calculating this column, you add up all those values. In fact, if you're looking at your calculation and wondering, say, well, what cells did I click? Here's a little cool trick for you. So I've got this cell highlighted, or this one cell highlighted. If I click my formula, it'll highlight the cells that I'm adding up. It says, okay, you're adding up all these that I have in this dotted rectangle. So great, that's what I wanted. And then you can click this one and say, all right, what am I doing there? It says, oh, you're taking the square root of the one up above. So again, you can kind of look at both of those. And that's the way to go from the standard deviation, or the variance to the standard deviation. Now, out of curiosity here, let's see if we can apply our range rule. So let's go back to the range rule of thumb from chapter 4, or even chapter 3. The range rule of thumb talked about values that are significantly high, significantly low, and not significant. So significantly high, that was these numbers. Significantly high. That means you're above 2 standard deviations above from the mean. Significantly low, all right, well, we could do that one too. Significantly low, that's down here. That means you're below 2 standard deviations below the mean. And then you've got everything in between, values which aren't significant. So that's these right here. So a lot of times what we're going to want to calculate is mu plus 2 sigma and mu minus 2 sigma. And let's take a look at those. So I'm getting a lot out of this example. Now, it may be in place from my morning class. If it is, just delete the values under mu minus 2 sigma and mu plus 2 sigma. Let's calculate those for ourselves and see what we get. So in the first one, type in equals What was mu for this experiment? 7. In this case, it was 7 minus 2 times sigma. Sigma was the standard deviation, but you know what? I don't really feel like typing that in again. So I'm just going to click this one right here. That's the standard deviation. So mu minus 2 sigma, bam, about 2.17. Why don't you see if you can't calculate mu plus 2 sigma? See what you get there. Yeah, sure. So that calculation, there you go. 7 minus 2 times F17. And then do mu plus 2 sigma. And then we'll look at it and see what that means for this particular example. All right, while you're doing that, let me draw something out here for us. Draw out a number line with these different possibilities. And let's look at the results of our experiment. Now, when we're rolling a pair of dice, you can get a 2, a 3, a 4, a 5, 6, 7, 8, 9, 10, 11, and 12. Those are the possibilities that you get when you're rolling 2 dice. Let's take a look at what you got when we did your mu minus and mu plus 2 sigma. So let me zoom out a little bit here to get myself back in orientation. So I want equals 7 plus 2 times the standard deviation, which is an F17, and I get these numbers, 2.17 and 1.83. 2.17 and 11.83. I had a question here. You want to see that one? Sure. Equals 7 plus 2 times F17. Is your F17 got the same 2.4152 number that I do? If your calculation is off here, then that might be throwing things off for you. Let's look at what that means. First question first. Can I roll a pair of dice and get an 11.83? No. Nor can I get a 2.17. That's okay. This is just giving me the range for typical values. None of these values are significant. So these are your non-significant values right in here. So not significant is everything here. Basically from 3 to 11. These are not significant. What about a 12? What would you say about a 12? That's significant. In fact, it's significantly high. Significantly high. Okay. Over here, significantly low. There's only 2 rolls that are significant in this game. And it is a roll of a 2 or a roll of a 12. Those are the only ones that are significant. Everything else is not that uncommon that we're going to be surprised. But a 2 or a 12, yeah, those are surprising rolls. So, wow. Got a lot from that one. Okay. Let's keep rolling. No pun. are we okay with your calculations? And I know, Oz, you're struggling to get that 2 plus and 2 minus, or sigma plus, and did you figure it out?
I was on the wrong one.
Oh, okay. All right.
So don't use plus me like this.
Okay. Let's move on to example D, which is going to be a lot shorter, I think. And let me see. Let me go at it this way. When playing roulette at a casino, a gambler is trying to decide whether to bet $10 on the number 35 or to bet $10 that the outcome is any one of 3 possibilities, 0, 0, or 1. The gambler knows that the expected value of a $10 bet for a single number is minus $1.06. For the $10 bet that the outcome is 0, 0, or 1, there's a 3 in 38 probability of making a net profit of $30 and a 35 in 38 probability of losing $10. Find the expected value and then which bet is better. So I've got this already teed up for us in example D, our little tabs here, so let's click over to that. Here's your 2 outcomes. One thing that has to be true is that your outcomes have to be numerical values in order to consider this a probability distribution, and they are. Either you win $30 or you lose $10. Now I showed you the probabilities here in terms of fractions, but realistically, Google Sheets is not going to really like it if you use these fractions, so I put them in as decimals. Now let's calculate x times p of x, which I did here for you. What do I have to do now to calculate the expected value? Yeah, find the sum. Remember, the expected value, or the mean, is the sum of these things. So just add up those 2 probabilities, or those, no, not probabilities, those 2 products, equals sum. And then click both of those. So for example D, if you're betting on just any of those 3 numbers, your expected value, or on average, is what's going to happen is you're going to lose $6.84 every time you bet $10. Does that sound like a good bet? No. But the other bet, you're losing $1.06 every time you bet $1. If you're going to bet one of them, which one are you going to bet? Bet on a single number and lose $1.06, or bet on a trio of numbers and lose $6.84? Single number. Why the single number? Keep in mind, this is what happens on average. That's what the mean of these distributions represents, is what's happening on average. If you were to sit there and play this game thousands and thousands of times, on average you lose $1.06 every time you bet $10, if you're playing a single number. If you're playing this triple of numbers, then your expected value is minus 684. Ooh, that's way worse. You're losing almost 70% of your money every time you bet on average, as opposed to here, it's closer to 10%. So, yeah, betting on a single number is better. Betting on a single number is better. Let's stay with that theme for just a moment. And before I move on from this, are we okay with our answer here? That, yeah, if you're going to lose, I'd rather lose less money on average than lose more money. So, minus $6.84. Keeping that example in mind, I believe got another, I think it's example G. Let's see, is it example G or H? Yeah, it's example G. Let's just turn to it this way. And let me see if I can't make that a little bit bigger. 28. There we go. The Michigan Lottery runs a Keno game. And I'm not going to explain Keno now, but I went through and I calculated the expected values. Now, when you're playing Keno, you can choose to try and match 4 numbers, 5 numbers, all the way up to 10. Here's the expected values. Which spot looks like the best one to play if you were going to play the game? I'm going the 4 spot, right? But look at how much variability there is in your expected value. The 10 spot? Wow. On average, you're losing 3 times as much with the 10 spot as you are with a 4 spot. Yeah, I would stay away from the 10 spot for sure. The 4 spot looks the best because although you're losing money, signified by the minus here, it's not as much on average as you would if you're playing the 10 spot. So, okay, nice. Let's try another one, example F. And we're going to do the same thing here that we did with our example for rolling 2 dice. We're going to calculate the mean, standard deviation, and apply the range rule of thumb. So these are some of the things that I want you to get out of this session here today, is to be able to calculate these things. Now these probabilities here sound pretty off to me. I don't know that many people that sleepwalk, but let's take a look at this. Refer to the accompanying table, which describes the number of adults in groups of 5. So you have groups of 5, and you ask each group of 5, you know, how many of you report sleepwalking? And this is what I find amazing. So I don't know anybody who sleepwalks. I mean, there's nothing wrong with it, you know, that's fine, but it looks like about 67% of people, or 67% of these groups have either 1 or 2 people that sleepwalk. I'm like, that's an amazing number. I don't know. In any case, our goal is to calculate the mean and standard deviation of these groups and then use a range rule of thumb to identify significantly high and significantly low. So that's our goal. We can ignore pretty much the rest of this stuff and just focus on the goal. So let's see here. You know what? Let's example F. There we go. Whew. I was going to say, I thought I cleared these things out. All right, so I already calculated the mean for you. That's just the sum of these things times each other. So the mean is 1.48. What that's saying is that on average, 1.48 people out of a group of 5 reported sleepwalking. You can't really get that number if you're doing this experiment. You can't have 1.48 people out of 5. But this is the average. This is what happens across dozens and dozens and hundreds of groups. Use that mean to try and calculate the variance, standard deviation, and do yourself a favor here. Let's delete this. Start from scratch when you calculate mu minus 2 sigma and mu plus 2 sigma. Now, I'll walk around and try and help out. If you're having problems, let me know. But try and get to that mu minus 2 sigma and mu plus 2 sigma. See what you can do. calculate the items in column D. And I gave you the formula up here. You want P of X times X minus mu. There's one key in working with mu. What was that one key I said? You actually want to type in the number for mu, 1.48. Don't click some buttons and refer to that as part of your formula. Just type in the number itself. Otherwise, you're going to run into problems. Well, you can't. You can't edit it? Keep the first formula right. Yeah. So you see that little.
Oh, the little dot.
Little dot. Drag that in there.
Oh, okay, cool. Thank you.
You're welcome. No, you don't want to type in the number, you want to type in X. So it's going to be P of X, which is here. You want to click these cells for X and P of X.
Oh, okay.
So P of X is X. Yeah, you need B2 there. B2, you need parentheses. So that's, yeah, that's between A2 and then around the 1.48. So that.
Is it name?
Good.
I do.
You should be able to do this in Google Sheets. I don't think there's any advertising in Google Sheets.
Yes, no, you're right. I have to step outside to take care of this advertising thing, but it's still, I
Okay.
turned it off midway. Okay.
Okay.
I'm just asking for the formula.
But what's the difference between A2 minus 1.4? Because it's the same thing, it's zero. Just the regular numbers. Because see, A2 is zero. Oh, no,
It should be P of X, which is in B. Dash times X minus 1.4.
Pretty much giving me error. It says name. This is what it did.
Well, you have to calculate that by first calculating the variance. So you got to do all this stuff. You got to fill in that column.
Thank you.
So now I left it. So I got the sum set up for you in the square root, but um,
This is about to piss me off.
should be P of X, which is B2 times. Oh, you gotta type in the variable here, X minus 1.48. It's not the number zero. It's the variable. Mm-hmm. 1.03.
So now it's gonna be for zero.
All right.
What'd you put in? Can I use your light? You say you're keeping. Put 1.48.
All right. So let's take a look at this. You can type in equals, and then I want P of X in column B, times, parenthesis, and then X The only number that you actually type in is the mean itself. So that'd be minus 1.48. 1.48. Oz, can you hold up a second? Raised to the second power, like that. So that's your calculation. Let me zoom in a little bit so you can see that. That should be what you set up for the first one. You get that one right, the rest of them should follow. Enter. Now, it didn't give me that option to follow it all the way down, so grab this little ball here, click and drag. When you do this for yourself in your homework, you're going to have to realize that, oh, okay, it's the sum of these that gives me the variance. So if you take a look at this cell, if I click this, it's summing up these here. From there, once I got the variance, I want to take the square root of that to get the standard deviation. Last but not least, I want the mean, which is going to be equal to 1.48 minus 2 times, and for this part, I'm just going to click this cell. There. And then I'll repeat that for equals, and the mean, which is 1.48, plus 2 times the standard deviation. And there's other more clever ways I can do that, but we're okay with that. Let's look at those on a chart and try and make sense out of those 5 numbers. So the numbers I want to write down to keep track of are negative 0.56 and 3.52. So the possibilities that we could get from this experiment were anything between 0 and 5. All right, so let's write down those possibilities. So that was 0, 1, 2, 3, 4, and 5. That's how many people in a group of 5 that we could see as sleepwalkers. Now, significantly low started here at negative 0.56. Significantly high started here at 3.52. What's that say about significantly low events? Is it possible to have any significantly low events occur here? No. No, because you can't have anything less than negative 0.56 when you're talking about the number of people in a group of 5. So there's no significantly low events. Are there significantly high events? 4 and 5. Those are the ones that are significantly high. Everything else, 0 through 3, those are just not significant. Nothing is extraordinary is happening there. All right, the only thing I didn't get to do that I really wanted to was talk about this one, example B. The short answer in this is that the more extreme answers are the ones that you want to pay attention to when you're looking at these kinds of probabilities. I'll let you look at that one at home. I'll be happy to answer some questions on it next week. But I got to get you out of here now. So, see